In 1896, a French physicist named Henri Becquerel stumbled upon a mystery that would change the world. This was a time of great scientific curiosity and exploration, and Becquerel was at the forefront of this wave of discovery. He was studying the properties of uranium salts, a substance that had intrigued scientists for its unique characteristics. Becquerel was particularly interested in their ability to fluoresce or glow when exposed to sunlight. This phenomenon of fluorescence had been known for some time, but the exact mechanisms behind it were still a subject of research. He conducted an experiment where he placed uranium salts on a photographic plate, expecting them to create an image only when exposed to light. But something extraordinary happened. The results were not what he had anticipated. The uranium salts left a mark on the plate even in the dark. This was a completely unexpected outcome, suggesting that there was an unknown source of energy at play. Becquerel realized that the uranium salts were emitting a powerful form of energy that could penetrate through opaque materials. This energy was unlike anything that had been observed before. This mysterious energy was not related to fluorescence, but something entirely new. It was a groundbreaking discovery that would have far-reaching implications. He had discovered radioactivity, a phenomenon that would unlock the secrets of the atom and usher in the atomic age. This was a pivotal moment in the history of science. Becquerel's discovery opened a new realm of scientific inquiry. Researchers around the world were inspired to explore this new form of energy and its potential applications. It challenged the existing understanding of matter and energy. The discovery of radioactivity suggested that atoms, once thought to be indivisible, could release energy in ways that were previously unimaginable. The world would never be the same. The discovery of radioactivity set the stage for a series of scientific breakthroughs that would transform our understanding of the universe. The implications of Becquerel's finding were profound. It opened up new possibilities for scientific research and technological innovation. It suggested that atoms, once thought to be indivisible, could release tremendous energy. This was a revolutionary idea that would lead to the development of new theories and technologies. This discovery paved the way for a new understanding of the universe and our place within it. It challenged scientists to rethink their theories and explore new frontiers. It also laid the groundwork for technologies that would revolutionize medicine, industry, and warfare. The applications of radioactivity were vast and varied, impacting many aspects of modern life. But with this newfound power came a heavy responsibility, one that would test humanity's wisdom and resolve in the decades to come. The ethical implications of harnessing atomic energy would become a central issue in the 20th century and beyond. Intrigued by Becquerel's discovery of mysterious rays emitted by uranium salts, Polish physicist Marie Curie and her husband Pierre Curie embarked on their own groundbreaking research on radioactivity. They were fascinated by the potential of this new form of energy and were determined to uncover its secrets. The Curies worked in a makeshift laboratory, tirelessly processing tons of uranium ore to isolate the radioactive elements responsible for this mysterious energy. Their lab was far from the sophisticated facilities we see today. It was a drafty shed with rudimentary equipment, but their determination was unwavering. Their relentless efforts led to the discovery of two new elements, polonium and radium, both far more radioactive than uranium. These discoveries were monumental, as they not only expanded the periodic table, but also opened up new avenues for scientific research. Marie Curie coined the term radioactivity to describe the spontaneous emission of energy from these elements. This term has since become a cornerstone in the field of nuclear physics, encapsulating the essence of the phenomena they were studying. The Curie's research was crucial in establishing the fundamental properties of radioactive decay. They meticulously documented their findings, providing a comprehensive understanding of how radioactive elements behave over time. They demonstrated that radioactivity was an atomic phenomenon, independent of external factors like temperature or pressure. This was a groundbreaking revelation, as it suggested that the source of radioactivity was intrinsic to the atoms themselves. Their work had profound implications for physics, chemistry, and medicine. It challenged existing scientific paradigms and paved the way for new theories and applications that would revolutionize these fields. The Curies' dedication to their research came at a personal cost. They often worked long hours under harsh conditions, and the physical toll was evident in their worn-out appearances. They exposed themselves to dangerous levels of radiation, unaware of its long-term effects. The lack of understanding about the hazards of radioactivity meant that they took no precautions, leading to severe health issues later in life. Despite the risks, their passion for scientific discovery never wavered. Marie Curie, in particular, continued her research even after Pierre's tragic death in 1906, driven by an unyielding commitment to uncovering the mysteries of radioactivity. Marie Curie's pioneering work earned her numerous accolades, including 2 Nobel Prizes, making her the first woman to receive the prestigious award and the only person to win Nobel Prizes in 2 different scientific fields. Her achievements were not just personal triumphs, but milestones for women in science. Their legacy continues to inspire generations of scientists, a testament to the power of human curiosity and the enduring impact of groundbreaking discoveries. Modern researchers often cite the Curies as their inspiration, and their methodologies continue to influence contemporary scientific practices. The Curies' work laid the foundation for our understanding of nuclear physics and paved the way for countless applications of radioactivity in medicine, industry, and beyond. From cancer treatments to energy production, the practical uses of their discoveries are vast and continue to grow, underscoring the lasting significance of their pioneering research. While the Curies were busy unraveling the mysteries of radioactive elements, their groundbreaking work was just the beginning of a new era in science. Another scientist, Ernest Rutherford, was hard at work trying to understand the very structure of the atom, a quest that would lead to monumental discoveries. Rutherford, a New Zealand-born physicist, conducted a series of experiments that would revolutionize our understanding of matter. His curiosity and determination drove him to explore the unknown. Using alpha particles emitted from radioactive materials, he bombarded a thin sheet of gold foil. This experiment, known as the gold foil experiment, was meticulously designed to probe the inner structure of the atom. At the time, the prevailing model of the atom was the plum pudding model, which suggested that atoms were composed of a diffuse cloud of positive charge with negatively charged electrons embedded within it. Rutherford expected most of the particles to pass straight through, with only minor deflections. However, to his astonishment, some of the alpha particles were deflected at large angles, and a small fraction even bounced straight back. This was a completely unexpected result that challenged the existing atomic model. This unexpected result led Rutherford to propose a new model of the atom. He realized that the atom must have a small, dense center that could repel the positively charged alpha particles. He envisioned a tiny, dense nucleus at the center of the atom, containing most of its mass and all of its positive charge. This nucleus was surrounded by a cloud of negatively charged electrons orbiting at a distance. The nucleus was surrounded by a cloud of negatively charged electrons orbiting at a distance. This new model provided a clearer picture of atomic structure and laid the groundwork for future discoveries. Rutherford's nuclear model of the atom was a radical departure from earlier models. It fundamentally changed the way scientists viewed the atom and opened up new avenues of research. It explained the scattering of alpha particles and provided a framework for understanding the nature of radioactivity. This was a significant leap forward in the field of nuclear physics. His discoveries laid the foundation for the development of nuclear physics and our understanding of the fundamental building blocks of matter. The implications of his work were vast and far-reaching. His model also opened up a whole new set of questions. Scientists began to wonder about the composition and behavior of the nucleus itself. What exactly was this nucleus made of? What held it together? These questions spurred further research and experimentation. And could this enormous energy locked within the atom be harnessed? The potential for harnessing atomic energy became a tantalizing prospect for scientists and engineers alike. These questions would drive further research, ultimately leading to the development of nuclear weapons and nuclear power. The exploration of atomic energy would bring both incredible advancements and profound ethical dilemmas. Today, the legacy of Rutherford's work continues to influence modern science. Researchers around the world build upon his discoveries, pushing the boundaries of our knowledge about the universe. From particle accelerators to quantum mechanics, the quest to unlock the secrets of matter remains at the forefront of scientific inquiry. Rutherford's pioneering spirit lives on in the hearts and minds of scientists everywhere. As we continue to explore the mysteries of the atom, we are reminded of the importance of curiosity, perseverance, and the relentless pursuit of knowledge. The journey to understand matter is far from over, and each discovery brings us one step closer to unlocking the ultimate secrets of the universe. In 1938, two German chemists, Otto Hahn and Fritz Strassmann, made a discovery that shook the world: nuclear fission. Building on the work of Fermi, who believed he had created heavier elements by bombarding uranium with neutrons, Hahn and Strassmann conducted their own experiments. They bombarded uranium with neutrons, expecting to create new, heavier elements. However, their results were puzzling. Instead of finding heavier elements, they detected the presence of lighter elements, such as barium, in the products of their experiment. This was completely unexpected and challenged the prevailing understanding of nuclear reactions. It was Lise Meitner, a physicist who had collaborated with Hahn and Strassmann before fleeing Nazi Germany, who provided the key insight. Meitner, along with her nephew Otto Frisch, realized that Hahn and Strassmann had actually split the uranium atom, a process they called nuclear fission. They calculated the enormous energy released during this process, confirming its incredible potential. This discovery, born out of meticulous experimentation and brilliant insight, would have far-reaching consequences, forever changing the course of human history. The world was on the brink of war, and the potential of nuclear fission as a weapon was immediately apparent. The race to harness this power, for better or worse, had begun. It would lead to the Manhattan Project, the Cold War, and the precarious balance of nuclear deterrence that defines our world.